Assembot is a robotic manipulation system that performs automatic assembly of target structures. Using Assembot, we can create depictions of simple objects out of cubes. Our system architecture comprises of several components. We start with an input image and pass it through an image-to-blocks algorithm. This gives us coordinates for goal cube placement locations. Then, our system takes scattered blocks and estimates their poses using ICP to derive cube start locations. We pass this information into a trajectory optimization algorithm, and finally, the robot assembles our desired object. Our Drake simulation environment comprises of a KUKA-IWA robotic arm placed on a table, several blocks scattered on the table, and some obstacles for the robot arm to avoid, in this case a Christmas tree. We created these obstacles manually in Blender and converted them into SDF files. The first component of our pipeline is an image-to-blocks algorithm. We take an input image and derive block locations. We start with an arbitrary input image with a large object centered in the middle. Then, we use the deep learning segment anything model to obtain segmented versions of these images by specifying bounding box around the desired object. This model does not work perfectly and there are a couple of artifacts, but it doesn't make a large difference in our final results. From these segmented images, we obtain object masks. And then, we downsample these masks to get pixelated objects, and pass them through a threshold to get block locations. In this example, we show block arrays comprising of 16 by 16 blocks. However, the KUKA-IWA is too small and is not mobile, so it cannot handle such large drawings. So for the purposes of our robotic arm experiments, we downsample the images to be 4 by 4 blocks instead.
We use trajectory optimization to move scattered cubes to their goal positions given by our image-to-blocks algorithm. For now, we assume the system knows the ground truth scatter positions. Later, we will discuss using post-estimation to approximate them. For the longer paths, such as from start to pre-grasp, we use kinematic trajectory optimization as we only care about getting the gripper from point A to B quickly. For fine-grained grasping and placing motions, we use IK to solve for the orientation of the gripper as well. We then stitch the trajectories together. The first challenge is solving for the kinematic trajectory with other free bodies in the same plan. The solution is to constrain the position and velocity for free bodies, then reconstruct the final trajectory using only IWA control points. Now we can move the gripper from point A to B. The second challenge is to handle fine-grained grasping and placing motions. The solution is to use IK to solve for both position and orientation of the gripper. The left video fails to pick up the cube using only kinematic trajectory, but the right video picks up the cube nicely with IK added. The third challenge is producing smooth trajectories. Linking kinematic and IK trajectories elegantly solves the problem. When transitioning from kinematic trajectory to IK, we use joint positions to query the final pose of the gripper and pass it to the start of IK. From IK to kinematic trajectory optimization, we set the IK final joint positions as the initial guess of kinematic trajectory optimization. This gives us a smooth trajectory, and the IWA robot arm is able to pick and place the cube elegantly. We can also add a minimum distance lower bound constraint to enable collision avoidance. The IWA arm successfully avoids the cube welded in space with collision detection. Solving these three challenges, we're able to have the IWA pick up 4 scattered cubes and make a simple pattern.
Now, since we have an optimized kinematic trajectory, we delve into some practical simulation to real issues like adding vision processing to our project. We scattered the cubes randomly and estimated the poses by implementing a pose estimation pipeline. In this pipeline, we used a depth camera to gather the point cloud of the background without the cubes and the point cloud of the background with the cubes. Using this data, we segment the point cloud of the cubes. Then, along with the ground truth poses of the cubes and model cloud point, the segmented point cloud is added as input to the ICP block, which finally generates the estimated poses of the scattered cubes. In this pipeline, we developed the segmentation algorithm from scratch. The segmentation algorithm has 2 major steps. In the first step, we mask the points belonging to the cube. In the second step, we remove the outlier with the help of setting a threshold distance from the centroid of the cube. The final outcome of this algorithm is the segmented point cloud of the cubes. One of the major challenges of this implementation was to get a good convergence from ICP. By tuning the initial poses, adding outlier removal, and setting correspondence from model to world while estimating the poses help us to generate better convergence. Here, we demonstrate the convergence of the initial gaze to the ground truth point cloud of the cubes. Another major simulation to real challenge of our project was fine-tuning the contact forces of the scene objects. Point contacts use minimum penetration distance to determine force direction, resulting in non-physical discontinuities. As a solution, we use the newest edition of Drake hydroelastic contact calculations. As demonstrated here, while stacking cubes using point collision, there was significant instability, which has been solved using hydroelastic contact with the illustration of contact force and an associated contact patch. We evaluated our system by quantitative evaluation for pose estimation error, qualitative evaluation for object-to-object contact force behavior, and accuracy of goal object construction. We successfully constructed goal structures like alphabet A, M, and S. Also, we constructed a few complex structures like a house and a banana. We also successfully evaluated the full pipeline using pose estimation and collision avoidance on some of the goal structure. In a nutshell, the major limitation was the failure of trajectory optimization in a few cases and requirement of initial gaze for ICP. Thus, in the future, we want to mainly focus on including deep perception and force-driven control to facilitate building complex 3D structures using our system. We get to learn about DREC and solve a fun problem through this project. Looking forward to extend it into real worlds. Thanks.